Now let's look at a reflective wave. Here we have this first red wave. Now using the TWTT formula, small d equals V times T divided by 2, they can calculate the depth of the water. In this calculation, they are going to measure the sound wave emitted from the gun, but this time, instead of measuring the travel time to the last hydrophone in the string, they measure the travel time to the first. In addition, they will now vertically measure the radial direction travel time of the sound wave as it reflects off the bottom. Their timing device reports that the total travel time is 0.45 seconds, but they only want to measure the reflective time, so they divide their total travel time by 2. Going back to the formula, capital D equals V times T, they now must account for the two-way travel time, so our formula will read small d equals V times T divided by 2. Putting in their numbers, they write small d equals 1,480 meters per second times 0.45 seconds divided by 2. Doing the math, they know that little d equals 333 meters. So the depth of the water is 333 meters. By plotting this line in red, we measured the depth of the ocean. This is what they call seismic data with no processing. This means that they make no corrections for noise, angles, etc. We use the data exactly as it is recorded. We will call this the x direction, and it represents each hydrophone and its distance from the source. Y represents TWTT, or two-way travel time, for each hydrophone. Using computers, we can measure and then plot the wave as it moves out to each hydrophone. By looking at the x's and y's, we can see the overlaps from the various hydrophones. These impressions, or lines, represent different rock boundaries. As I have illustrated, seismic technology allows us to see into the subsurface by using sound wave properties to illustrate formation characteristics such as rock type, depth, and shape, map the subsurface structures. Now that we know the fundamental properties of seismic technology, let's discuss the three phases involved in the science of sound waves that help us in our decision of where to drill the first well. The names of the three phases are data acquisition, data processing, and data interpretation. Like their names imply, data acquisition is where we get or collect the information. Data processing is where we use the data we acquired to make measurements and calculations, and data interpretation is where we analyze, evaluate, and make conclusions about what all the data means or signifies. In data acquisition, we go into the field, on land or offshore, to actually make measurements with our seismic equipment. Let's look at the equipment used to first create seismic waves and then to record them. There are several types of equipment used to generate and record seismic waves, depending on the surface and subsurface location, composition, and conditions. We'll begin with the equipment called the energy source. The energy source is used to create a sound wave. There are three types of sources. The first is the air gun. It is used offshore in water. The second is dynamite. It is used on land, typically in wetlands like jungles and swamps. The third is a vibrator mounted on trucks. It is typically used on land in dry conditions like deserts where the soil is loosely compacted. The next piece of equipment is called the receiver, and it is used to record the sound waves. The receiver used on land is called a geophone, and the one offshore is called a hydrophone. Both have a timing device to measure the time the sound wave traveled from the energy source to the receiver. In making the recordings, for instance on land, we direct the explosion into the rock and then measure how fast it comes back. If the sound travels through hard rock, it will come back much faster than if it is soft rock. Let me mention one last tool that is used in data acquisition. Ocean Bottom Cable, or OBC. This seismic tool permits surveys to be done after the offshore field has been developed. When a seismic ship can no longer pull the traditionally 4-kilometer long string of hydrophones through the congested offshore rigs and platforms, an ocean bottom cable is used. This OBC is designed to be laid or dragged on the ocean floor and contains a series of geophones, not hydrophones, that are normally used offshore. We used all of this equipment to acquire data to computer centers to process the acquired data. This phase is called data processing. They use computers to make very sophisticated graphs using filters to remove background noise and other unwanted effects. Here are some examples of graphs that have been created using the data from these receivers. They allow us to visually illustrate the formations and rock types below the Earth's surface. Let's review. You have an energy source that emits a sound wave. You fire, vibrate, or explode the energy source and then measure how long the sound wave takes to get back to your measuring device called a receiver. In other words, you measure the time the sound waves take to bounce back to your receiver, like measuring an echo. Sound waves travel through hard rock, like igneous and metamorphic, at different rates of speed than soft rock, like sedimentary rock. You can record these subsurface echoes that bounce back from the different rock types. The time for the echo to return gives us a way to determine the rock boundaries or the places where rock type changes. As we move our source and receivers around on the surface and take the new echo measurements, we can collect data that is then fed into computers that allows us to describe the shape of the rock formations below over a large area. We can illustrate this data on 2D or two-dimensional maps, as well as in 3D, three-dimensional, and 4D, four-dimensional maps. 2D maps have X and Y coordinates. They appear flat on a page. Three-dimensional models have an X, Y, and Z coordinates. They appear lifelike, like the images our brain sees. They are images with depth. With these facsimiles, we can see the structures, the closures, the way fluid flows, where the oil, water, and gas come together at the contact lines. By compiling the images in three-dimensional models, we can better visualize what is there. In 4D maps, we compare 2D and three-dimensional maps over time. Let me give you an example. Here we have a producing field with its pertinent data represented in an image. In 4D, we look at that same field 3 years later, maybe after we have extracted oil from the formation and have more exact data. We compare the available data to see if there has been any changes over time, and if so, what those changes are. We also look for changes that can help predict future production forecasts. Therefore, in 4D, we have width, height, depth, and time.